dear students of class 7. Today we will be discussing about molecular orbital theory. So in our previous video we had discussed about hybridization and its applications, and before that we had discussed about atomic orbital theory, or we had discussed about atomic orbital theory. Now we will be discussing about molecular orbital theory. So molecular orbital theory tells us that whenever we have two atoms of comparable energy, the orbitals of atoms, whenever two atoms they come together, and if they possess similar or comparable energy, then they combine to produce molecular orbital. Now once molecular orbital is produced, the atomic orbital, it loses its identity. Now from atomic orbital, it will be converted into molecular orbital. So there are certain 7 features of molecular orbital theory. So please listen to it carefully. Now these molecular orbitals are the reason, okay, where you have the maximum probability of finding the electron. So molecular orbitals may be defined as the region in the space in which an electron is most likely to be formed. Second point, molecular orbitals, as I told you, are obtained when atomic orbitals they combine. Number 3 point, when a set of atomic orbitals combine to form molecular orbital, then the number of atomic orbitals will be always equal to the number of molecular orbitals. Suppose 1s of different atoms they are combining, that means 1s of one atom and 1s of another atom. If they are combining to form this molecular orbital, then you will be having how many molecular orbitals? 1 plus 1 will be 2. 2 molecular orbitals are obtained. The next point is the atomic orbitals, one from each atom, combine to produce 2 molecular orbitals. Now, one of these will possess lower energy than the atomic orbital, and the other one will possess more energy than the atomic orbital. Suppose you have this side, as you go up, energy increases. Now suppose you have 2 atomic orbitals. Now these are 1s orbital, say 1s orbital. Now if this atomic orbital, AO means atomic orbital. This is one atomic orbital of an atom, and this is another atomic orbital of another atom. Now if they are combining to form molecular orbital, then what will happen? Here 1 plus 1, you will be getting 2 molecular orbitals, out of which one will be having higher energy. Okay, so one of them will be having higher energy, the other one will be having lower energy. So these two are now molecular orbitals, which are generated from the combination of these atomic orbitals of these 2 different atoms. Now whenever you compare atomic orbital was having this much of energy, here you can see it. Now once they combine to form molecular orbital, one is having lower energy than this atomic orbital, and this is known as bonding. Okay, and this is anti-bonding orbital. This is anti-bonding. Anti-bonding orbital, molecular orbital will have higher energy. Please remember, and this, the one having lower energy than atomic orbitals, it is known as bonding orbital. Okay, so the next point. Now, each molecular orbital, can you see that? Each molecular orbital can accommodate at a maximum of 2 electrons. It cannot have beyond that. So each molecular orbital can have at the most 2 electrons. Now, the molecular orbitals, as in case of Babu principle, the different this S, P, D orbitals, they were arranged according to what? Increasing energy level. Here also, in case of molecular orbital, the orbitals will be arranged according to the increasing order of energy. And whenever you have 2 degenerate molecular orbitals, you must have not forgotten. That means you still remember Herd's rule. Then, if 2 orbitals are there, then first they have to be singly filled. Yesterday we had discussed about that. First they have to be singly filled, then only the pairing takes place. Here also in case of MOT, that is molecular orbital theory, if you have degenerate orbitals, then these orbitals should be filled with electron singly first, then only the pairing takes place. So these are the 7 features of MOT. Now let's discuss about energy level diagram for molecular orbitals. Okay? As you had school, public school, that arrangement, here also in case of energy level diagram for molecular orbitals, there are certain pattern, that there is certain sequence, okay, that you need to know it properly. So here, energy level diagram for energy level diagram for molecular orbitals. Now from hydrogen, or we can say lithium to nitrogen, we have a sequence of these molecular orbitals. Okay, the lowest energy level molecular orbital is sigma 1s, then comes sigma 1s star. Similarly, after that we have sigma 2s, then comes sigma 2s star, then comes pi orbitals, pi 2px, which is equivalent in energy with pi 2py. After that comes sigma 2pz. After that we have pi 2px star or asterisk, which is in equal energy with pi 2py star. And at last we have sigma 2pz star orbital. So we have this sequence. The lowest in energy is this, then this is the sequence of molecular orbital in an increasing order of energy. That means 1s, sigma 1s will be the lowest one, the lowest molecular orbital. Okay, you have to remember this sequence. From here, the questions will be asked. This sequence. So at first 1s, then comes 2s, then comes 2px, 2py, then 2pz, then asterisk of this 2px and 2py, then asterisk, this is star of 2pz. Now here we have to listen to it very carefully. This, wherever you have this asterisk sign or star, that is the anti-bonding molecular orbital. That means whenever, I told you, whenever atomic orbitals are combining, then one will be having high energy, the other one will be having lower energy. The asterisk one or the star one are the anti-bonding molecular orbital, and wherever you don't have this asterisk or star sign, then that is the bonding molecular orbital. Now this is true for lithium to nitrogen. Okay, this sequence you have to remember it. Now for oxygen, fluorine, and neon, you have a slightly different this sequence of molecular orbitals. Here, this sigma 2pz comes before this pi orbitals. Okay, here this is just a small change in case of oxygen, fluorine, and neon. Okay, so hope you will be able to write the sequence. So let me write it: sigma 1s, sigma star 1s, sigma 2s, sigma 2s star. Then comes sigma 2pz. Then comes 5 2px, which is equivalent with energy with 2p1. Then after that you have pi star 5 2px star, which is equivalent with energy with pi 2py star. And you have at last sigma. So the last one I'm writing here, sigma 2pz star. So the sequence for these three elements, oxygen, fluorine and neon, is this. Okay, so you have to remember it properly. Now don't be confused. It's like this is one orbital, one molecular orbital, and it has maximum capacity of holding 2 electrons. Each of them has maximum capacity of holding 2 electrons. It cannot accommodate more than 2 electrons. Now here you can see, in this case, in this example of this part here, these two are, this is one molecular orbital, this is another molecular orbital, and since they are having what? Equal energy, equal to sign, you can say it. That means whenever you are filling the electrons, then since these two are now degendered orbital, degendered means what? They are having the same energy. That means this also has maximum capacity of 2 electrons, and this can hold maximum of 2 electrons. So whenever you are filling the electrons, first of all, it will be filled like say 1, 1. Single, it has to be, Hertz rule has to be followed. Since it is equivalent in energy, that means first it will have 1 electron, and if you have more than that, then it cannot accommodate both electrons. It will be wrong. So 1 electron here, then it goes to the another orbital, then 2, then 2. Maximum capacity is 2. Hope this is understood. Here also the same thing. So let me explain with one example. Suppose you have oxygen molecule. Oxygen is, its atomic number is 16. Since 2 electrons, 2O2 is there, that means in total how many electrons are? In total 8 plus 8 is 16 electrons. So this 16 electrons, if you want to fill it up, will you take this sequence of energy orbital or this sequence of energy orbital? Please don't be confused. If you write this 16 electrons in this sequence, the upper one, then it will be wrong. This is not for oxygen. For oxygen, fluorine and neon, you have to fill the electrons in this sequence. Okay, let's remember this. So 16 electrons, 2, 4, 6, 8, 9, 10, 11, 12, 2, 4, 6, 8. Okay, so up to that point we have done 8 plus 2 is what? 10, 2, 12, 12 plus 2, 14. Okay, 14 electrons are filled up to this point. Now after this, which atomic orbitals are there? Anti-bond atomic orbitals of 2px and 2p1. Then here, up to here it is 14. Yes or no? 2, 4, 6, 8, 10, 12, 14. Then, if you write 2 electrons over here, that means it is equivalent to 16, but it will be wrong. I told you why? Because these orbitals, you can see equal to sign, these 2 orbitals, molecular orbitals are degendered, means they have same energy. Therefore, first they have to be singly occupied. So 1, 1. So 1 plus 1, 14 plus 2 is what? 16. Now this is your correct sequence. This is the correct sequence of filling the electrons. Okay? Have you written 2 over here, 2 here, then it will be wrong. You will get 0 for that. So please, you have to be very careful. This is very simple, but there are certain points that you have to remember. So while filling the degenerate orbitals, it has to be single effect. Hope this is clear. Now let's draw this molecular orbital diagram for this sequence and this sequence. Okay, one of the sequence I'll be doing, the other one you can learn from the previous whatever I'll be teaching it, and you can do it by yourself. So this sequence is very, very important. Okay, please remember it. So let's take sequence for oxygen, fluorine, and neon. I'll be doing this. The other one you'll be doing as your assignment. So for this, what you have the sequence? The lowest one is what? Sigma 1s, then comes sigma 1s star, then comes sigma 2s, then sigma 2s star, then you have what? Pi 2px, which is equivalent with energy 2py, then you have sigma 2pz, sigma 2pz, sigma 2pz. After that we have pi 2px, which is equivalent energy with 2py, and here we have anti-bonding orbitals. Then comes sigma 2pz star. So this is the sequence for oxygen, fluorine, and neon. So you have to remember this part. Okay, this is for what? This is for not oxygen, fluorine, and neon. See, you'll be confused. Therefore, I have written this sequence here. This sequence you write it for oxygen, fluorine, and neon, it will be wrong. Here, what you have to remember? You have to remember this sigma 2pz. This comes when? It comes before this pi orbital. Okay? So please, this part you have to remember it. If you make a slight mistake, means you will not be given any marks. So after sigma 2s star, what comes? Then comes sigma 2pz orbital. Sigma 2pz orbital. Then only comes pi 2px, which is equivalent with energy with pi 2py. Pi 2py. So this is the sequence of energy. This is the sequence in energy for molecular orbitals. So now, from this sequence, you can see that the sigma 1s is having the lowest energy. So whenever you have atomic orbitals, you have to take two atomic orbitals. Okay, so this is 1s, this is 1s. Now whenever they combine to form molecular orbital, one will be having higher energy, the other one will be having lower energy. Okay, so this is 1s, these are atomic orbitals. This is also atomic orbitals, and this in between is the molecular orbitals. Okay, then this is 1s, then comes 2s. So these are 2s atomic orbitals. Now this again will have bonding and anti-bonding. So these are 2s. So up to this point we have done it. Okay, then comes this p orbitals. Now in p orbitals you have three boxes. That means three boxes are there. 1, 2, 3. 1, 2, 3. So this is 2px, 2py, and 2pz atomic orbitals. This is also 2px, 2py, and 2pz atomic orbitals. The name for each box is 2px, 2py, and 2pz. Now, see, out of this three atomic orbitals and these 3 atomic orbitals, 2 of this atomic orbital and 2 of this atomic orbital, that is 2px and 2py, they will combine and they will have what? Equivalent energy. Can you see that? And here, which one is having, see, out of this, again, these 3, here as atomic orbital, they are having the same energy, but once they form molecular orbital, their energy is varying. Can you see that? Here, the energy of this and this, 2px, 2px, 2py and 2pz is not same. Sigma 2pz is having lower energy. Therefore, here one orbital, molecular orbital, here will be, this orbital will be sigma 2pz. So let me write it, sigma 2pz. Then comes these 2 orbitals which are equally energy. So here again you will be having 2 orbitals which are equivalent in energy. Okay, so up to this point we are finished. This is having lower energy, sigma 2pz, then after that comes pi 2px and pi 2py. So this is your pi 2px and pi 2py. Now the anti-bonding of that, anti-bonding of these orbitals. Okay, so you have to remember this. Okay, the sequence. Once you remember the sequences, I wrote it. After these 2 orbitals, what comes? Then comes pi 2px and pi 2py, anti-bonding of that. So here, what we have again? These are anti-bonding orbitals. Pi 2px and pi 2py star. And at last, what you have? The highest in energy is what? The highest in energy is sigma 2pz star. So this is your sigma 2pz star. These 2 are pi 2px. This is equivalent energy with pi 2py. Now these are anti-bonding orbitals. Why anti-bonding? These were atomic orbitals. They are these molecular orbitals are higher in energy, and these 2 orbitals are descending. Okay, please don't forget. Now this is your pi 2px, which is equal to pi 2py. This I wrote it, and this is your sigma 1s. This is your sigma 1s star. This is sigma 2s, and this is your sigma 2s star. So as you go up, energy increases. So this is the molecular orbital diagram for which elements? For oxygen, fluorine and neon. Now if you have to fill the electrons for oxygen, that means